Welcome to our university booth at DAC 2012. In this video we will demonstrate some of the features of a GeCoS compiler framework developed by the Kern Research Group at INRIA and IRISA in France. GeCoS is a source-to-source compiler. It takes a C program as an input and produces a transformed C program as an output. Such compilers are common in high-performance computing and are often used for automatic parallelization purposes. However, these tools have rarely been used as front-end optimization engines for C2 hardware compilers. The goal of GeCoS is to fill this gap by providing a complete source-to-source framework targeted toward high-level synthesis backend with a focus on Catapult C. To this end, GeCoS provides an extended C front-end with support for arbitrary sized integers and fixed-point format data types through the motor graphics algorithmic templates. GeCoS is script-driven and let users define highly customizable transformation flows. Our first example shows a toy program consisting of several calls to a function multenadd along with some pragma directives. These directives state that all calls to the add function should be inline, whereas only one specific call to the mul function should be considered for inlining. The source-to-source flow is defined in a GeCoS script file that uses the .cs extension and contains a sequence of calls to GeCoS compiler passes. After running the compiler script and refreshing the srcgen folder, we observe that it now contains a modified version of the original program, where inlining operations have been performed according to the directives. Let us now show more advanced examples that demonstrate the capabilities of a GeCoS loop transformation framework. It is widely admitted that nested loop kernels are very good candidates for hardware acceleration and form the hotspot of most signal processing applications. However, deriving an efficient hardware implementation out of a loop nest with a high-level synthesis tool can be challenging, and the designer must generally resort to sophisticated loops and/or layout source code transformation. The goal of this transformation can be to expose fine-grained parallelism to enable loop pipelining, to reorganize how data is distributed in memory banks to avoid conflicts, or to take advantage of spatial and temporal locality through a custom memory hierarchy built out of scratchpad memories. To illustrate the role of these transformations, we will start by a simple example. In this small kernel, statement S0 and S1 cannot be executed in parallel because of a data dependency from S0 to S1. However, this dependency can be removed through a simple loop shifting operation for S1. In the GeCoS loop transformation engine, such a transformation is expressed using pragma directives. In our example, we add a directive to each statement to specify the transformation to be applied. Detailing the formalism behind these transformations is out of the scope of this demo. In this example, we choose a transformation so as to keep the same order execution for S0 and shift S1 by one iteration of a loop as illustrated by the I+1 expression. Let us now run the GeCoS compiler script. After a few seconds, we obtain our transformed source code, which is now amenable to software pipelining. Of course, this transformation is quite obvious, and one can wonder whether it actually needs to be automated. Let us therefore look at a more complex example that consists of two cascaded image convolution kernels. These two kernels are combined to implement a Gaussian blur image filter that can be used for image restoration purposes. If used as is in an HLS tool, the two-loop nest of the algorithm will be executed in sequence, even though a designer can easily figure out that the execution of this two-loop nest can be pipelined. To enable pipelining, the designer has to resort to a fusion of a two-loop nest that can be expressed using our loop transformation engine, as shown in our example. However, ensuring that the transformation is legal can be tricky. For example, the fusion that we just implemented turns out to violate non-obvious data dependencies and alters the behavior of the program. This violation is easier to understand with a data dependency graph. In our case, the violation comes from the fact that we use TMP of I and j+1 before its first definition, one iteration away. Such dependency violations are detected by the GeCoS analysis framework and are directly reported to the user through the Eclipse user interface. In our example, to be legal, the fusion must be performed jointly with the loop shifting by at least two iterations along dimension j. The legality of a transformation is then confirmed by our analysis framework. To learn more about GeCoS, you can visit the GeCoS webpage hosted by the INRIA GForge. You will find detailed installation instructions, several tutorials, plus a mailing list and some bug report tool. Thank you for your attention.